Hi class, welcome to lesson 23, the third and final video looking at the history of the atomic structure. We will still learn more about the atomic structure, but this is the last video covering the history. In today's video, you will learn to describe the Bohr ring model of the atom. You will relate the distance of an electron to the energy of an electron in an atom. And you'll describe the quantum mechanical model or the current model of the atom and describe how it differs from previous models. Make sure you take notes as you follow along. If you have any questions, write them down and bring them to class. Today's video is building upon the big idea that the modern model of the atom evolved over a long period of time through the work of many scientists. Today, we're going to look at the scientist Niels Bohr and the many scientists who made the quantum mechanical model of the atom. Niels Bohr accepted the Rutherford model of the atom. This is called the nuclear model of the atom, where the center of the atom has a small, dense, positive nucleus, and there are randomly arranged negative electrons outside throughout the atom, kind of like. Niels Bohr did an experiment called a flame test. What he did is he took various atoms and put them in fire. He observed that different atoms glowed different colors within the fire. He later went and separated this color of light with a prism. He used this to calculate exact energies of electrons. So his model of the atom suggests that there are electron rings, also called principal energy levels. Electrons travel in these fixed paths or orbits along these principal energy levels. He noted that electrons closer to the nucleus have less energy. Electrons absorb energy to move to higher energy levels, also called the excited state. The further from a nucleus an electron is, the more energy it has. When electrons return to the lower energy level, they release a characteristic and specific amount of light called a quanta.
What is up, everyone? In this video, we're going to talk about the emission spectra of atoms and also the Bohr model of the atom. The Bohr model was the first of its kind because it was the first model to suggest that the energy of electrons is quantized, meaning that the energy of an electron in an atom is limited to certain discrete values. And it's the emission spectra of atoms that led to this model. So what exactly is an emission spectrum? Well, it all originates from how atoms behave when they absorb energy. When atoms absorb energy in the form of heat, light, or electricity, oftentimes they're going to re-emit that energy in the form of light. These images show light emitted by nitrogen, neon, and krypton atoms. Notice that each element gives off its own characteristic color of light. But why? Well, if we inspect this light more closely, we'll discover a very revealing clue that shows how electrons exist within atoms. By now you probably know that passing light through a prism will separate the light into its constituent wavelengths, but unlike the continuous white light spectrum that is observed from the sun or a light bulb, the spectrum of light given off by atoms, the so-called emission spectrum, is composed of specific bright lines with dark spots in between. This type of spectrum is called a line spectrum. Each element has its own unique emission spectrum. Think of it like a fingerprint. In the same way that a fingerprint can be used to identify a person, an emission spectrum can be used to identify an element. In fact, astrophysicists can identify the elements that make up a star by obtaining the emission spectra from the light given off by these stars. But how exactly did emission spectra change the way that we think about atomic structure? Well, Bohr proposed a model in which electrons could only exist in certain orbits at certain fixed distances from the nucleus. He also argued that the energy of an electron was also limited to certain discrete values. In other words, the location and energy of electrons is quantized. It's sort of like a ladder. Just as your feet can only stand on the rungs of a ladder, but not in between, electrons can exist only in these orbits, but not in between them. Furthermore, his model suggested that an electron orbiting a nucleus does not absorb or emit energy. It's only when an electron makes a transition or a jump between orbits that an electron absorbs or emits energy. Electrons absorb energy by jumping from an orbit of lower energy to an orbit of higher energy, while electrons emit energy by jumping from an orbit of higher energy to an orbit of lower energy. The amount of energy absorbed or emitted is simply the difference in energy between the two orbits. Since the electrons are never observed between orbits, the jump from one orbit to another orbit is instantaneous. The electrons literally teleport between orbits. Let's examine the emission lines of the hydrogen spectrum. A transition from the third orbit to the second orbit emits red light at a wavelength of 656 nanometers. A transition from the fourth orbit to the second orbit emits blue-green light at a wavelength of 486 nanometers. Jumping from the fifth orbit to the second orbit emits blue-violet light at a wavelength of 434 nanometers. And finally, a jump from the sixth orbit to the second orbit emits violet light at a wavelength of 410 nanometers. Notice that as the energy of the transition increases, the wavelength of the emitted light decreases. There are several more transitions that occur within the atom, but only the ones that we just discussed emit wavelengths of visible light. All other transitions emit light with wavelengths that lie outside of the 400 to 700 nanometer range of the visible spectrum. Nevertheless, only certain specific amounts of energy are emitted as an electron relaxes to a lower energy orbit. These packets of energy, also called quanta of energy, are emitted in the form of photons, or light particles. Only a series of photons with specific energies, there are only going to be specific wavelengths of light that show up in an atom's emission spectrum. And that's why we get a series of bright lines instead of a continuous white light spectrum. So the Bohr model had a lot of explanatory power, but a lot of questions were still unanswered, like why electrons could only exist in certain fixed orbits. Well, it turns out that these orbits are actually the result of electrons behaving as waves, and we're going to expand upon that in another video. The Bohr model is not the model that we currently accept today, but it's still really important because it served as an intermediate model between the classical understanding of the electron and the fully quantum mechanical interpretation. The Bohr model was eventually replaced by a more advanced quantum mechanical theory that completely included the wave behavior of the electron.
In addition to knowing that each electron on a ring has a specific amount of energy, you also should know that each ring can hold a specific number of electrons. The first ring with the lowest energy closest to the nucleus can hold a maximum of 2 electrons. The second ring can hold a maximum of 8 electrons, while the third ring can hold 18, and the fourth ring can hold 32 electrons. Electrons always fill in the lowest possible energy. The lowest energy is not always the maximum number of electrons. All of the electron configurations provided on your periodic table are those of atoms. Additionally, those are the lowest possible configuration for the electrons of those atoms, otherwise called the ground state. Please take a moment to pause the video to jot down these very important notes about the Bohr model of the atom. Although the Bohr model is not the most current model of the atom, its ideas about the energy of electrons are still valid, and we will rely heavily on these ideas throughout the year. Here is a Regents question testing your understanding of the Bohr model. A characteristic light is emitted by these ions in a flame when the electrons, every time we see emit, we know this is a loss of energy. So the electrons emit energy as they return to lower energy levels. When electrons in the excited state return to lower energy state, the energy emitted can result in the production of spectra. Remember that some spectra are visible, like the lights above our heads, and other spectra occur in the non-visible wavelength. Here, we are looking for the electron configuration of a sulfur atom in the ground state. Recall that all the electron configurations on your periodic table are for atoms, and they are all in the ground state. When we look at sulfur, we see that its atomic number is 16. Therefore, there should be 16 electrons in its configuration. When we look at the matching configuration, we can see that choice 4 is the best choice. The current model of the atom uses modern quantum physics to describe the wave nature of the electron. This model was developed by many scientists, and this model suggests that atoms include a positive dense nucleus, mostly empty space, and electrons are found in a cloud called an orbital, which is a region that you can probably find an electron most of the time. It is very important that you take note that electrons are not believed to be in orbits, as described by Bohr, but instead orbitals, or clouds, as described in the current quantum mechanical model. Here is a Regents question to test your understanding of the quantum mechanical model or wave mechanical model. The region of most probable location of electron is called an orbital. Never choose orbit for the probable location of an electron. That concludes lesson number 23. If you have any questions, bring them to class. As you know, we'll do more practice in class. See you soon.